All right, so I'm going to go over some basic integrals, and I'm going to show you a couple techniques on how we can solve and find the antiderivatives, so to speak. Okay, so first we have the integral of the square root of x dx. So a good idea here is to rewrite this using exponents. So we have the integral of x to the 1/2 dx. This is just like, when you're differentiating, and it's easier to differentiate when you can see the value of the exponent. So here, we basically are just going to use the, anti-power rule. So instead of multiplying by 1/2 and then, subtracting 1 from the power, we're going to add 1 to the power. So we're going to get x to the 3/2, and then we're going to divide by that power, and then add our constant c, and then we just simplify. So the antiderivative would get as 2/3 x to the 3/2 plus c. All right, for b, we have the integral of pi over 2x squared dx. Now, let's not let the pi and even the 2 confuse you, because the pi and the 2 are just constants and they're just actually coefficients. So this is just essentially like pi over 2 times 1 over x squared. So this is, again, pi over 2 times 1 over x squared dx. And the pi over 2 can actually come out because it's a constant coefficient. So it can actually just be pi over 2 times the integral of 1 over x squared. And again, you rewrite this as x to the -2 because it lets you see the power more easily. And then we just use the reverse power rule. I like to call it the reverse power rule, anti-power rule. So instead of multiplying by this, we're going to first add 1 to the exponent and then divide by that. So we're going to have pi over 2 times x to the -1 divided by -1 plus c. And then so our answer will be negative pi over 2x plus c. All right, for c, again, don't let that 2 throw you off. This is the same as just 2 times sine of x dx. So we can actually take the 2 out and have this be 2 times the integral of sine of x dx. So let's just focus on the antiderivative of the sine of x. So again, just doing the opposite. What function has the derivative that's the sine of x? And that's going to be the negative cosine of x. So this will be 2 times the negative cosine of x, or just -2 cosine of x. Let's not forget our constant c. All right, d. I know this one looks a little weird. We just have the integral of dx. But think of this as just the integral of 1 dx. So think about what function has a derivative of 1. And that's just going to be x, because again, it's just like 1, x is 0. Remember, number 1, we don't write number 1 usually, but writing it out lets you see what's going on. So this will be x plus c. And again, you can always verify your answer by taking the derivative. If you took the derivative of this, you'd get that the derivative of x is just 1 plus 0, and that's what you get here. All right, for e, all you have to do here is take the derivative of x and take the derivative of 2. Now, it's common for like textbooks and, like for integrals not to be written as like a group. So even though technically it is being multiplied by dx, you're not going to see parentheses around the integrand. But just understand that it's just the same as, polynomial expression here. Anyway, so the antiderivative of x, remember this is the same as x to the 1. So we do x to the 2 divided by 2 plus the antiderivative of 2, which will just be 2x. And don't forget your constant. The constant, again, is a big deal. Some teachers and professors will take off points, and they're really strict on it about it on the AP exam. All right, F. Okay, here we got, again, a polynomial, and again, just technically it is all being multiplied by dx, but usually won't be written that way, but just know that technically it is. So we just take the antiderivative of each of these, just one by one. So remember, it's 3x to the fourth. So we add 1 to the power, so 3x to the fifth, and divide that by 5. Minus 5x to the second, add 1 to the power, so 5x to the third, and divide by 3, plus x to the 1, so add 1 to the power, x to the 2, divided by 2, plus your constant c. And do try these on your own. I forgot to mention, try these on your own, pause the video, try these first on your own, then, unpause it once you think you got an answer. I'm obviously going to not pause it because I don't want to waste time, but, try this on your own first. Okay, next one we got, okay, now this is a good one. So we have the integral of x plus 1 over the square root of x. Here, it's going to be helpful to break it up. So this is the same as the integral of x over the square root of x plus 1 over the square root of x. Now, remember, x over the square root of x, the square root of x is x to the 1/2. So this is the same as x to the 1 over x to the 1/2. So this first part will just be the same as x to the 1/2, just using the exponent property. And this is just like 1 over x to the 1/2, which is the same as x to the negative 1/2. So when you break it up like that, it's more easy to integrate because then you just integrate each term one by one. And you can see that the first one will be x to the 3/2. You add 1 to the exponent, so x to the 3/2 divided by 3/2 plus x to the adding 1 to the exponent, x to the 1/2 divided by 1/2 plus c. And then just simplifying, you'll get 2/3 x to the 3/2 plus 2x to the 1/2 plus c. All right, h. Okay, this is a good one. So here we're gonna break this up as, the integral of the sine of x over the cosine of x times 1 over the cosine of x dx. Now we do that because then you can see that this will be equal to sine of x over the cosine of x, the tangent of x, times 1 over the cosine of x is the secant of x, as you should know, dx. And then if you have your integrals or your derivatives down, you should see or know that this is actually the derivative of the secant of x. So then the answer would be the secant of x plus c. And that's because, again, if you take the derivative of the secant of x, you're going to get tangent of x times secant of x. All right, for I, remember this is the same as the integral of 2 over x to the 1/2 dx, which is then going to be the same as 2 times x to the negative 1/2 dx. And then we just use the reverse power rule. You get 2 adding 1 to the exponent, 2x to the 1/2 over 1/2 plus your constant c. And simplifying, you'll get 4x to the 1/2 plus c. All right, for J, we got an example of a integral where it's be helpful to expand. So remember, this is the same as t squared plus 1 times t squared plus 1 dt. So what you can do is just multiply this out and expand it as a polynomial. So you would get t to the 4th plus t squared, so plus 2t squared plus 1 dt. Then from here, you can just integrate term by term. From here, you can then go that this will be the same as adding 1 to the exponent, so t to the 5th over 5 plus 2t, adding 1 to the exponent, 2t to the 3rd over 3 plus t plus c. And there you go. All right, for k, this is another example of where we want to break this up. So you can break this integral up as x cubed over x squared plus 3 over x squared dx. All that is being multiplied by dx, technically. And then we can rewrite this. You go down here as the integral of x cubed over x squared is just x. 3 over x squared is the same as 3x to the negative 2. And then we can just integrate term by term. X is the same as x to the 1. So adding 1 to the exponent would be 2. Dividing by 2 then, plus 3x, adding 1 to the exponent, 3x to the negative 1 over negative 1 plus c. All right, and for this last one here, we can rewrite this as the integral of, remember, this is the same as the 3rd root of x times x minus 4 dx. And we'll just multiply the x and the minus 4 by x to the 1/3. So this is the same as x to the 4/3 minus 4x to the 1/3. Then from here, we can use the reverse power rule. Add 1 to the exponent here, but we're going to get x to the 7/3 over 7/3 minus 4 times adding 1 to the exponent minus 4x to the 4/3 over 4/3 plus c. And let me see, I'll try to squeeze this in here. Simplifying, we'll get 7/3 x. No, we'll get, that's 7/3 x. I have to cross this out. I'm going to put this answer over here. And that's going to be 3/7 x to the 7/3 minus 3/4 4 minus 3 x to the 4/3 plus c. That is what I meant to do. And there you go.